Okay, let's get started. Today we're going to continue talking about the BRMS R package, continuing what we were doing on Tuesday. Also throw in a little bit of R. Consequently, have to say that as an employee of Columbia University and also someone who uses STAN for business purposes while Columbia is seeking additional grants to develop STAN further, those two facts imply appearance of conflict of interest needs to be disclosed in presentations such as this one. So to start off today, want to talk about a type of model that is extraordinarily prevalent in the social sciences, that being ordinal models. And this is a generalization of Bernoulli models that we have talked about before, when instead of there being only two categories, now there are J categories. J is at least two. Ordinarily, if you're going to use one of these models, would be three or more, although R lets you do it with two. And the critical thing about a model like this is you're conceiving of the categories as having some sort of order to them, and this is often the case for survey research, survey questions where the answers typically take some sort of form of like Likert scale, where you sort of strongly agree, or neutral, or disagree, or strongly disagree with one of the questions on the survey. But in general, it could be, something like small, medium, or large. In a model like this, we're usually going to remove the intercept, although different software does this in different ways. And we have to estimate a vector of cut points, which I will call gamma. This vector is of size j-1 if you take the intercepts out. And we're thinking of an observation mechanism where the observed y is in the first category. If another unknown value y star, which can be interpreted as utility and can be a linear or even a nonlinear function of predictors. In any event, if utility is less than the first cut point, then the observation falls into the first category, which could be like strongly disagree. If the utility falls between the first cut point and the second cut point, then the observation comes out in the second category, like, disagree but doesn't strongly disagree, all the way up to the last category, which is said to occur if utility exceeds the j-1 cut point. And so that person would answer strongly disagree. So the unknowns in this model are y star, the utility values, even though y star is usually going to be a simple linear function of predictors, in which case we have unknown coefficients, but we also don't know what the cut points are, how much utility you have to go from, strongly disagreeing with something to disagreeing with something. And you could allow these cut points, or any of the parameters, really, if you're doing this from a Bayesian perspective, to differ from one group of people to the next, or even from one person to the next. All sorts of different things can be done to yield a model for these unknown utilities, and then seeing where they fall relative to the unknown cut points, and estimate the joint posterior distribution of all these unknowns. The utility values have error in them, and the error distribution in principle can be anything, but the two most popular choices are to use standard normal distribution for the errors, in which case you get a so-called ordered probit model, This can be estimated by Gibbs sampling, and if you look at some of the outdated literature on how to do a Bayesian model like this, they will be using Gibbs sampler. It's fairly easy to estimate without Gibbs sampling using Stan these days, but certainly there's a series of papers about how to do this from a Bayesian perspective using Gibbs sampling. The other one that is popular is to use a standard logistic distribution for the error values going into utility. That yields ordered logit model. As far as I know, that can't be estimated using Gibbs sampling. Not that it matters. You could estimate either one of these using Stan, and it doesn't make a whole lot of difference between them. The logistic function related to that can be evaluated a good bit faster than the probit ones, but the probit ones, it's a little bit easier to deal with some extensions, some missing data stuff, some things like that. Certainly more common in economics, whereas the logistic model is more common in statistics. Both of these, if J is exactly 2, and so you have 2 categories, they simplify to conventional binary probit model, binary logit model. However, in that case, we usually fix the only cut point to be 0 and estimate intercept. As we'll see in a second, you know, the intercept and one of the cut points are basically interchangeable because you could shift one by some value and shift the other by the same amount, and you would get exactly the same distribution of observed values y. So questions about a setup like this or its applicability to social science? Okay. So despite how prevalent a model like this, or at least the frequentist version of a model like this is in the social sciences, most social scientists would be hard-pressed to really write down the data generating process in code. And, you know, most of this would be pretty much the same if you were to estimate one of these models using a frequentist estimator, but they would still be hard-pressed to write down the process for generating, you know, frequentist point estimates. So, you know, we'll do the Bayesian version here using a Stan function. So this is going to return a matrix. The matrix is going to have S rows and N columns, one for each of the observations that we are drawing from the prior predicted distribution of. So the arguments to this function are S, the number of simulations we want to do, J, which is also an integer, the number of categories in the outcome variable, so the number of possible things that the respondents to the survey could say. Matrix X of predictors, this is going to be N by K. In this setup, like we referred to on the previous slide, it's not going to have a column of ones to estimate the intercept, and instead we'll estimate J minus 1 cut points. Kind of a vector of scale for the coefficients in this model, assuming you're going to use like normal 0 with expectation 0 priors. What would be the scales that you want to use there? Also, real number, positive real number, indicating what scale you want to use for the gaps in the cut points here under your prior. So between gamma 1, gamma 2, between gamma 2, gamma 3, etc. So we start off by pulling out N, which is the number of rows in X, K, which is the number of columns in X, and setting up a matrix that's S by N to hold our prior predictions, given X. Also going to create L, which is a Cholesky factor, but in this case, it's just a diagonal matrix that's going to be going into my normal prior. On the coefficients, I should have put diag matrix beta scale here, but I forgot I passed myself the beta scale parameter, so I just put in ones here. So this is basically equivalent to if my beta scale had been 1, 1, 1, 1, 1. That has a size k. Then I'm going to make a vector of zeros, which is going to be my expectation for the prior on the coefficients in this ordinal model. This can be created in the standard language using the rep underscore vector function. So this is going to make a vector of size k, and it's going to fill it the same value in each cell of that vector. In this case, I give it 0, and that's going to be used throughout. So that's all the preliminaries. I start the loop over the number of simulations, so s equal 1, s equal 2, up to s. Each simulation, I'm drawing a vector of size k, in this case from a multivariate normal distribution, with expectation being a 0 vector, and the Cholesky factor of that multivariate normal distribution being the aforementioned L, or maybe L that has beta scale on it instead of a vector of ones. Since L is technically a Cholesky factor, but it's also diagonal, so that implies that my beliefs about the elements of beta are independent of each other, which is probably not the most plausible thing. However, a lot of people find it very difficult to specify. They know that the elements of beta shouldn't be independent of each other, but they have a lot of difficulty specifying exactly how the dependence should be, particularly when they only have sort of a covariance matrix to do so. And so assuming those are independent is not the worst thing in the world. I mean, in a manner of speaking, lack of dependence is sort of equally, in the middle between having positive dependence and negative dependence. Certainly in the posterior distribution, you can see how your posterior beliefs of these things are correlated once you condition on the data. But here we're just trying to draw data and see how plausible the resulting ordinal realizations look under our priors. So we're using normal prior for beta. Then we construct eta, which is a vector of size n, equal to x, which is n by k, multiplied by beta, which is a vector of size k, resulting in a vector of size n, essentially being our linear predictors for the model. Now, this is going to use logistic distribution on the errors, and so you can think of eta as the log odds. So remember, odds is like the probability of something divided by the complementary probability. And here, the odds ratio in question, the numerator is the probability that the outcome is less than or equal to category J, and the denominator is the probability that the outcome is greater than category J. And this model asserts that the logarithm of that odds ratio is a linear function of the predictors. And so this setup is often called a proportional odds model, because a difference of 1 unit on one of the predictors among people who are otherwise the same is going to have the same effect on the log odds, irrespective of what J is. So again, numerator is the probability the outcome is less than or equal to category J. Denominator is the probability that the outcome is greater than category J. That's an odds ratio. The logarithm of the odds ratio is a linear function of x, but it's a linear function of x that does not depend on what the exact value of J we're talking about is. So the odds ratio for like, you know, the third category less than or equal to the third category divided by the probability that it's greater than the third category is the same linear function as the log odds for the probability you're less than or equal to the second category divided by the probability that you're greater than the second category. In any event, eta is not particularly interpretable under any circumstances with a generalized linear model or, you know, anything that is nonlinear. And so the coefficients that you get back are in these, you know, units of log odds, which a lot of people have considerable difficulty interpreting. Unlike a lot of other models where people can't interpret the coefficients, well, they can at least fall back on, you know, I can say whether it's positive or negative. I can say whether it's statistically significant or not. In a model like this, actually, X only has an unambiguous monotonic effect on the extreme categories. So, you know, if you have some predictor and it has a positive coefficient, let's say in reality, if I change your X to X plus 1, that may make the probability that you're in category 3 go down, but it makes the probability that you're in the jth category go up, and it makes the probability that you're in the first category go down. But the intermediate categories, you know, the proportion falling in them can go, you know, either up or down when the coefficient is positive, and the same as if it's negative. And so that makes it even more difficult to interpret these resulting coefficients as they are. But nevertheless, we can do what you're always encouraged to do in STAN, is to make plots of how the posterior probability changes for specific manipulations of the X variables. And so if you get the posterior distribution that corresponds to the unknowns of a model like this, you can, you know, easily say how the probability changes, but it doesn't change in an unambiguous fashion for the interior categories. Anyway, here we're still drawing from the prior predictive distribution. We've got our prior on beta, and that results in a linear predictor. We now need to construct gamma, which is the vector of cut points. I said previously we're going to estimate j minus 1 of those, and that's because we set the first value to be negative infinity. Then I'm going to set the second value equal to draw from a normal distribution, expectation 0, standard deviation passed in from the outside. And then for category, you know, 3 up through j, I basically have a random walk deal here, where the realization for category j is equal to the realization. It's not exactly a random walk because it's strictly positive, but it's equal to the previous cut point plus some draw from an exponential distribution with scale 1, which is guaranteed to be positive, multiplied by another positive number. So gamma 3 is going to be strictly greater than gamma 2, and gamma 4 is greater than gamma 3, etc., where the gaps between consecutive cut points have an exponential prior in this generative model. So we got our coefficients, we got our cut points. These are common to all observations, the way I've written this model, although you can certainly do this with hierarchical structure. You have, you know, different groups, stuff like that, the things we talked about on Tuesday and last week. But now we're ready to loop over all the observations, just assuming that there's no group structure here. We initialize integer to 1. We draw the error from the logistic distribution. With scale 1, we create utility for the nth person by taking their linear predictor and adding on the realization of the error. And then we do a loop as long as you are greater, well, first of all, as long as little j, is less than the number of categories, then it evaluates the second part. And it says as long as y star is greater than the next category, increment this up. And then when that while loop condition fails to hold, then you now have a realization of the outcome that you can stick into the matrix. When you're done with both of those loops, you can return the matrix of realizations from your prior predictive distribution back, and you're going to get a matrix that's S by N, where each column has a series of ordinal realizations for each person that is in X. Questions about that? Robert.
So that while loop, we're just figuring out which.
Yeah, where
they have the highest probability.
Yeah, where it not so much where it has the highest probability, but where you trip over the cut point. So where does y star fall in relation to these cut points here?
Okay. Is that not the category that? Is that not the category with the highest probability of being?
No. So I mean, you're going to have basically a simplex of probability over the j categories. Now, just because the highest probability for you personally is in category 3 doesn't mean that you're guaranteed to be in category 3. It means we're basically taking a draw from a categorical distribution with these probabilities. And you can get the probabilities out of that. We didn't show it here, but like I said before, we have this log odds thing. The probability you're less than or equal to this divided by the probability that you're greater, but the logarithm of that. So you do E, now you get an odds ratio, then you can convert from odds ratio to probability. So if there's 4 categories, your probabilities may be, let's just say to keep it simple, 0.1, 0.2, 0.3, and 0.4. Those are 4 numbers that add up to 1. And so you have a 40% chance of landing in the 4th category, but 40% chance is certainly not 100% chance. Right. So you're getting a realization from this probability mass function that's for you, given your x's, 0.1, 0.2, 0.3, 0.4. And so some of the realizations from your prior predictive distribution are actually going to be 1, indicating that you're in the lowest category. But on average, over the prior predictive distribution for your column, you're going to get, approximately 40% 4s, 30% 3s, 20% 2s, and 10% 1s. Other questions about the data generating process for a model like this? So we can see this in sort of graph form. This is being used with standard normal utility. I did standard logistic on the previous slide. So we have a standard normal PDF here in black, and we have vertical red lines indicating not necessarily equally spaced cut points. And so if your utility value falls below the first cut point, which looks like negative 1.25 or so, if you're in here, that means your observed value is going to be 1. If you're between here and here, your observed value is 2. If you're between here and here, your observed value is 3. If you're between here and here, your observed value is 4. And if you're over here, the observed value is 5. And consequently, the probability of your being 5 is the amount of area to the right of the last cut point under a standard normal distribution. That's a little bit easier to see if we look in terms of the standard normal CDF. I've put the cut points in the same place, and so you can see here that you have about a 0.7 something chance of being less than or equal to the last cut point, indicating a probability of 0.7 something that you're less than or equal to the fourth category, and perhaps a probability a little bit over 0.25 that you're in the highest category, given your x's. So the way that this model has been set up, everyone has the same cut points. We could relax that assumption fairly easily, but everyone has different x's, and consequently, even if the betas are the same for everyone in your data set, because everyone has different values of x, you're going to have different values of utility, and consequently, you're going to have different people falling, their utility values relative to these cut points. But we have to estimate those cut points along with the coefficients. Questions about those pictures? Okay. So the likelihood for a single observation is, you can think of it as multinomial. Probably would have better had I said categorical, because for each person we're only observing one realization of this process. But the likelihood function of the coefficients, the likelihood function also depends on the cut points, but I didn't explicitly write those here. It's just the probability multiplied over all j categories that you fall in the jth category raised to a power. This should be indicator function for y equal j. So when you actually are falling in the jth category, we're raising this to the power of 1. If you don't fall in the jth category, we're raising it to the power of 0. So that's just 1. And so the only term that actually contributes to the likelihood function is for the realized value of y, where, whether we're doing this with the frequentist maximum likelihood estimator or we're doing this in Stan, we're ultimately going to be using the logarithm of the likelihood. And so that is going to be equal to the log of the probability that you're in the category that you're in. And so since these are probabilities, these are bounded between 0 and 1. Another way of writing this is to sort of take the linear predictor plus realization of the error and say, is that less than or equal to the jth cut point? And that looks like a CDF. Indeed, CDFs are used to perform that mapping. And if you're in the scale location family of CDFs, like the normal or the logistic, you can write this as sort of the standard version of the CDF of the cut point minus the linear predictor divided by sigma, which is the standard deviation of the errors. But when you do that, you immediately see, well, if I just multiply the cut points by some positive constant, multiply the coefficients by some positive constant, multiply sigma by positive constant, then those A's are all going to cancel out. And that implies that the data don't provide any information as to what sigma is. You could multiply all the utilities by 12, and you would get the same distribution of outcomes in the data. And so that's just another way of making a point that economists make all the time, that utility doesn't have units. And so consequently, it's really only a relative measure of preferences for, this or that thing that's questioned, put to you on a survey. So this is just another way of saying that the standard deviation of the errors is not identified by the data. It could be any positive number, and you get the same observed values of y. Consequently, we just fix sigma to 1, which is what I did when I was doing the data generating process here when drawing from the error term. And then under that assumption, we can estimate the betas and the cut points, which is what we're typically interested in doing. So you can estimate a model like what I previously described using the stan_POLR function in the rstan_arm package, which was intended to have syntax similar, or at least for the first couple arguments, identical to the POLR argument or function in the mass package. POLR stands for proportional odds logistic regression, which is what, way back in the day was implemented in the mass package to do. However, subsequent iterations of that package added other ways, other basically link functions, CDFs, that you could use to make that transformation from linear predictors to probabilities that are specified in this method argument. So method could be probit rather than logit or logistic, whichever one it is, in which case you definitely have an ordinal model, but it's not a proportional odds model if you're using the normal CDF for the transformation, and it's not a logistic regression. So POLR is kind of a misnomer. It does include the ability to estimate a proportional odds logistic regression, and that's certainly the thing that statisticians are most inclined to do, but it also estimates ordinal models that are not proportional odds, but nevertheless have this sort of single linear predictor. So I've specified method equal probit to use a normal error assumption. Like stan_LM, stan_POLR takes a prior on the R squared for the model. Now, this is a little bit more difficult to do than in a typical linear model, because you're basically saying, well, what proportion of the variation in utility can be explained by a linear model with these predictors? In this case, like I said before, the standard deviation of the errors is fixed to 1. And so you're basically saying, okay, if the error variance is 1, what is the variance of x times beta, relative to that? So that's a little bit harder to think about, because utility is sort of this, construct that social scientists, assume people to have, but it's not something that you could observe. As we said before, it doesn't really have well-defined units, and so it's a bit harder to think about what will be a reasonable prior on the R squared for a model like that. But basically, in the social sciences, you can't get too low for an ordinal model. It is usually the case that whatever your predictors are, they're not going to explain very much of the variation in people's preferences. So even people who have the same age, the same income, the same race, the same education, etc., like that, are very likely to believe, very different things if you ask them, like, should the government lower taxes, or, something like that. And so for these kind of public opinion questions, it seems as if people don't even have that well-defined preferences over a lot of things. So the idea that social scientists could explain a lot of variation in what people's stated opinions are on questions that they may have never really seriously considered before seems to be pretty optimistic. And so if that's the case, you probably want to go with a fairly pessimistic prior on the R squared. But you can go higher if you want. This is a data set where people or somebody, maybe regulators, put ratings on the quality of inhalers for asthma or something like that. There was some kind of treatment, a new, even better inhaler than the previous inhaler. Presumably that was randomly assigned. Something about the period in which the study was conducted, whether the person is actually carrying the inhaler regularly. That comes from a data set in the BRMS package. Anyway, we can estimate the posterior distribution of the coefficients for that model. And then, once we have those coefficients, we can go on to ask ourselves questions. And, typical thing to do, particularly when you have an experiment or, really anything with a binary treatment variable, is to say, okay, well, what if everyone was treated? Get the probability of, the posterior probability of the ratings in that scenario, and then ask, well, what if everyone was in the control group? How would they, rate their inhalers? Get the posterior probability of those. I shouldn't have used, well, so yes. I shouldn't have said probability. Here I'm actually getting the posterior distribution of utility rather than converting it into probabilities. But the idea is still the same. What's the utility if you're treated? How well do you, rate your inhaler? What is the utility if you're in the control group? How well do you rate your inhaler? And then, you can get the posterior distribution of each of those things, subtract one from the other, and summarize the difference. In this case, the difference in utility is fairly far away from zero in the negative direction. I don't know whether like 1 was the best rating or 4 was the best rating. Doesn't really matter. I suspect the former in any event. So the difference between those two tends to be negative. Now, this might seem a little bit unsatisfying to you because it's in units of utility, and how are you going to really explain that? Unfortunately, you don't have a whole lot of good choices here. There's a paper by Don Rubin and some of his colleagues a few years ago showing that under his potential outcomes framework for causal inference, there's really no average treatment effect that can legitimately be calculated on the observed outcomes or on the space of outcomes because those are not really metric variables. They're not ratio scale. They're not interval scale. They're just ordinal scale. And so if you say, okay, I'm giving this inhaler like 2 stars, that is not in a meaningful mathematical sense, twice as good as having 1 star or half as good as having 4 stars or anything like that. It's just better than 1 star, not as good as 4 stars. And so in order to calculate, average treatment effect like we typically would if you had, a continuous outcome or even a binary outcome where we just sort of take a difference in means, can't really do that for the outcomes because those are really just like words, 1 star, strongly agree, or something like that. You can do a difference in utility, but then you're sort of saddled with the fact that it doesn't have units. You could do these calculations with transform equal true, and now they would be in units of probability. But then again, there's not going to be a monotonic relationship between the treatment variable and the probability that you're in this or that, because the interior categories can go either way. So you can really just say something like, if you switch treatment from 0 to 1, the probability that you fall in like the best category is this much better than, if you stayed in the control group or something like that. Sebastian, you had a question?
Oh, I guess I was just thinking like, yeah, utility doesn't like is actually having an argument. So like utility and probably pressure ratings. So utility of 1 star to 4 stars, or from 1 to 2 isn't the same as from 2 to 3. I think in the same way, a lot of quantitative stuff has the illusion of being equal intervals just because we took measurements with numbers. But so for example, blood pressure, going up 1 unit blood pressure doesn't mean the same thing at different units of blood pressure. Like going from 95 to 96 isn't really the same as going from 128 to 121. Like the increasing risk isn't necessarily
linear.
The for your health isn't the same, even though we do use a numeric scale.
Right.
Same thing with temperature, like.
Yeah.
So. Like
I think in the case of like blood pressure or whatever, so at least we do measure it continuously. You're right that your risk of like a heart attack or something is not linearly related to your blood pressure value, but it could be non-linearly related to that.
Yeah.
Whereas for a lot of these things in the social science surveys, like we'll see one of them on the homework that I'll post tonight, you really just say like, you know, policy question. You know, do you think, you know, the government should raise taxes or something like that? And the answers that the people see are not even 1, 2, 3, 4. That's put on by the data collector after the fact. What the people who respond to that question see is, I totally agree, I kind of agree, I sort of disagree, and I totally disagree. So they are just seeing like words. Now for like storage in the 1970s, when, you know, computers had like a kilobyte of disk space, they encoded that as 1, 2, 3, 4 integers because that was like easier to store in smaller size, and they could, you know, pass them around on floppy disks and stuff like that. Totally not an issue today, but it doesn't make sense to think of these 1, 2, 3, 4s as integers. They're really just labels that correspond to legitimately collected data, but the data that the people who were asked the questions were providing, they just saw like little phrases. So with blood pressure, yeah, it's non-linear and it's kind of weird, but at least it's sort of numeric, like it's related to the number of like milliliters of blood pumping through. Whereas with the categories, there's really no metric to it. Becca?
So to me, the interpretation of this is just like it's negative, right? That's about as good as we can.
Yes, and the probability that it's positive is extremely low. Like there was 1 or 2 posterior realizations that were positive.
Why, if that is the best really interpretation here, why not just treat them like numbers and then not interpret the coefficients, and then just interpret the coefficient of like we did a linear model, and we had negative coefficients and therefore it's negative. Yeah.
So if you look at the treatment coefficient here, it's going to be negative as well. And if you look at the probability that the coefficient is positive, it's going to be extremely small. So for this, I agree that it's sort of not a whole lot better than looking at the coefficient. But again, this, I think, it's not like screaming the obvious from this, but this makes it clear that the utility values depend on all the values of X. Yes, like regardless of whether you're a man or a woman or you're rich or you're poor, you're going to have the same bump depending on whether you're randomly in treatment or randomly in control. And so that is taken into account by the sort of posterior Lindpred thing, whereas just looking at the coefficient isn't. Also, I could have done transform equal true and map these into probabilities, but then it would just sort of for every person, like, here's the probability you're in 1, here's the probability you're in 2, here's the probability you're in 3, here's the probability in 4. And how does that change depending on whether you're in treatment or control? So you might find the probability as like a better units than utility, but you have to deal with the fact there's as many probabilities as there are categories of the outcome. Whereas this is like a single number, but then again, so is the coefficient.
Would an alternative be to just do a normal logistic model where you have probability of being in category 1 versus any of the other categories, and then compare, like do each comparison?
Right. So remember, this was probit, but if I'd done logit, I'm essentially modeling what's the probability you're less than or equal to category J divided by the probability that you're greater than category J. But I'm making this sort of like very linearity assumption that that functional form does not depend on which J I'm talking about. Now, extensions of this model, which we'll talk about later, will allow there to be different coefficients depending on where, in the distribution you're following. And that can be, a more realistic model, albeit one that's harder to estimate with maximum likelihood and stuff like that. So you can relax those. What's not a good idea is to be like, okay, I got 5 categories and I understand like regular logit better than I understand ordinal logit. So I'm going to just take my 5 categories and be like 3 or higher is yes, and 2 and 1 is no, and then do binary logit. Because then you've just thrown away variation in the data and you're going to get less precise estimates of everything. And in the end, you're still going to get coefficients that can only be interpreted as a log odds. So, you're going to have to do something to make them, probabilities in order to interpret anyway. And you just introduced a whole lot more noise, like self-inflicted noise. But that is an extraordinarily common thing to see, not just in the social sciences, but a lot of other things. People get outcome and then they it's not even a transformation. They do like a coarsening of their measured outcome in order to feed it to the only estimator that they're comfortable with, instead of getting comfortable with a more appropriate estimator for that design. And so you'll see this in machine learning all the time, like, models for like finance or whatever. And so, you have over this time period, the stock of Apple going, all over the place, mostly up or whatever. And they'll just code that as like, today it went up and yesterday it went down. And it's just like ones and negative ones, because their like classifier, only works for binary things, and it's totally thrown away the magnitude of the changes that are ostensibly related to the predictors that they're using. Whereas like, even if it was substantively important, and it rarely is, like, did it go up or down as opposed to how much it went up and down? You could like do that using a Bayesian model, get the posterior predictive distribution of how much something goes up and down. And if your utility is really not related to the magnitudes, then just take those posterior predictions and discretize them at 0 if you want. But then you're at least getting like posterior predictions of the thing that arguably goes into your utility function, but it has the whole uncertainty. But the coefficients that you estimated for the underlying thing are going to be more precise, should be more precise, as a result of you using more informative data than if you discretize the outcomes at the outset and then conditioned on those getting less precise estimates of the coefficients and then carrying that forward. Sebastian.
I don't know anything about surveying.
It's messy.
Yeah, it seems really hard. Is there anything you do to deal with? Sometimes there's this assumption that like there's a different process to go from certain to uncertain in one realm versus in the other.
Yeah.
So, like,
we'll kind of talk about one of those that you can do in BRMS.
Okay.
So this is an R stain arm. Let's just see the coefficient. So yes, the posterior median of the treatment effects was negative, but we're estimating the cut points as well. So its posterior median for the difference between first and second is estimated to be 0.33, and then there's a pretty big gap between the cut point between dividing 2 to 3, which has a posterior median of 1.76, and then 2.27 for that. If you take the posterior predictive probabilities for someone who has average X's, you can see they have a much higher probability of being in category 1. Almost all the rest of the probability they're in category 2, and are very unlikely to be in category 3 or category 4. Of course, that's just a kind of thing for someone with the average X's. You could do that for someone with particular X's and get the corresponding probabilities, and you could see how those probabilities change if you were to manipulate their sort of baseline X values in a particular direction. But otherwise, this looks a lot like it does for the other sorts of functions that are supported by RStanR. BRMS has a similar function, or it can estimate a variety of models that are similar. One thing that you can do with BRM that you cannot currently do with Stan Polar is use LME4 style constructs like this to allow the intercept or the coefficients or whatever to vary from one group to the next. So apparently these subjects were actually asked, over some period of time, like, how much do you like their inhaler? So here's a model with the sort of same linear predictor, but I'm now allowing my intercepts to vary from one subject to the next, and I have normal beliefs about those deviations before seeing the data. In order to estimate a model that corresponds to what Stan_Polar does, you need to specify family equal cumulative. So this idea, what's the probability that you're less than or equal to the jth category, that cumulative probability divided by the complementary probability. But you can estimate another model. This one has family S ratio for a so-called stopping ratio model. This is something that you don't see it used in political science that much. I think I've heard of it being used in sociology, where you're thinking of this data generating process is like, okay, someone, they start off, everybody's at least in the first category or whatever. And then they sort of choose, do I want to go on to the second category? And once I've made it to the second category, then they choose whether you want to go to the third category. But you could stop at every milepost and be like, okay, I'm satisfied where I'm at. I don't want to keep going on anymore. I don't know that that necessarily makes sense for public opinion questions. I have no idea if it makes sense for inhaler ratings, but you could sort of imagine like a model for, how high do you get promoted within your company? And so you can start off as like minimum wage, whatever. You could work your way up to some middle management thing and be like, okay, I'm happy here. I don't want to be like CEO. There's too many people complaining, so I'll just sort of stop. So for a model like that, maybe a stopping ratio would be better. I'm not going to show the data generating process for that, but that is one where you can wrap some of your variables in the CS construct, which stands for category specific, in which case the effect of treatment is going to be allowed to vary from one category to the next, whereas the effect of the period and whether you're carrying your inhaler is assumed to be constant across all of the categories. Again, we're going to have this intercept varying from one person to the next according to normal prior. Here I give an example of how you can call the set prior function to specify, okay, I have a normal prior with a mean of -1 and a standard deviation of 2 on these treatment effects. And that's going to be the same prior for each of the categories, but I'm not restricting the treatment effect to be the same across categories. I'm just using a prior that reflects that. Anyway, if you have two different models for the same outcome, you can use Liu information criterion to say which of those models is expected to predict future data the best. In this case, there's a slight preference for the second model using the stopping ratio likelihood and estimating separate treatment effects for each category compared to the first model here. But the difference is fairly small. It's not estimated overly precisely, so we can't really say we have a strong preference for one or the other. If you did like model weights, they would probably be like 40-60 or something like that. But in general, most of the things that you could do with a posterior distribution that you get from RStanR, you can also do with a posterior distribution produced by BRM they ultimately all come from Stan. The print of the model from BRM looks a little bit different. You know, it has sort of like what did you specify? Then there's like different chunks of output. The first one here is what Paul refers to as group level effects. So here, the estimate of the posterior distribution of how the standard deviation varies from one person to the next, and that has a posterior, forget if this is mean or median, but it's 1.26. You can see the effective sample size for this is lower than the effective sample size for a lot of the coefficients. This is something it's a bit harder to estimate. And then, so that's the sort of the standard deviation of the intercepts in the posterior. Then we have what he refers to as the population level effects. These would be the coefficients on X in the LME4 way of doing things. For, you know, the treatment, still negative, you know, the other things. What this says, intercept 1, intercept 2, intercept 3, that's really saying like the difference between cut point, or, you know, what first cut point, second cut point, third cut point, sort of thing. I don't know if intercept is the greatest terminology here. But anyway, you get output, and certainly if you did like as matrix, as data frame, whatever, you could get the raw draws of everything and, you know, do whatever you wanted in terms of analyzing it. You can pass it to launch Sinistan. You can pass the matrix of draws to base plot. You can make all sorts of plots like that. And so once you get to this point, there's basically not a whole lot of difference between how you obtain the posterior distribution, since it's sort of ultimately coming from Stan. If we do the print for the fit 4, which was estimated using the stopping ratio approach to ordinal models, we get, you know, similar stuff here, but we have treat 1, treat 2, treat 3. And so this first one here is sort of the treatment effect of, you know, category 2 going from category 1 to category 2. Second treatment effect is, you know, how much does the treatment influence your log odds of going to category 3 instead of stopping in category 2. And then, you know, the last one for the last category. And you can see, because there's not a whole lot of people in the 3rd to 4th category, the estimated standard deviation here is a lot larger than the whatever that is, posterior mean, posterior median. And so consequently, like a 95% credible interval is certainly going to include 0. And so we can say there's not really any evidence in these particular data to say, you know, what is the treatment effect of, you know, stopping at category 3 versus going on to category 4. Well,
Why is the
right. So these can be different. This is something that's always kind of troubled me, but these can be different. This is basically saying, okay, we're estimating this with the same precision as if we drew 369 times independently from this margin. Whereas like actual draws from the posterior distribution, they're dependent rather than being independent, but they're joint rather than being, you know, we have one set of draws for this margin, another set of draws for that margin, you know, et cetera. We just have these joint draws, and then we can point them into margins like that. And so you can get different effective sample size for the estimates of the posterior mean for, you know, it depends on what function that you're estimating. You usually see in these multi-level models that this will be estimated with like less precision and more dependence when there's not that many groups. Now, in this case, there seems to be like kind of a lot of groups or individuals who observed over multiple periods of time. So I don't think there's that much, but in this particular case, but ordinal models in general don't have nearly as much information in them as, you know, models with, you know, if we actually observe utility, we could, measure this all with a whole lot more precision. And so consequently, there can be, more weirdness to posterior distribution on one margin to the next. And that can show up both in, the estimated standard deviation and in the effective sample size. All right, so we got that. We talked before, maybe a bit briefly, that stan_gam4 and the rstan_arm package can estimate the effects of predictors that are arbitrary smooth functions of those predictors, and those fairly easy to estimate. You get full uncertainty, works way better than the machine learning version that uses the same syntax. But you can do all those things using BRM as well. And then one thing that you can do with BRM that you can do with rstan_arm is you can estimate a lot more models that have particular nonlinear functional forms, because those nonlinear forms really just get pasted into a Stan program and compiled. So Paul has an example of vignette. This is simulated data. So we have some coefficients. We have a X predictor. Then we're drawing from sort of standard normal with this conditional mean function, which is a nonlinear function of B2 and a multiplicative function of B1. Obviously, we could take the logarithm of y and make this into a linear model in log of B1 and B2 times X, but certainly can do a nonlinear model, bind those into a data frame, specify our priors on B1 and B2. And in this case, normal, you have to specify in LPAR, which do these pertain to. And then you just call BRM, wrapping the formula in the BF function, which I think doesn't stand for base factor. It stands for like BRMS formula or Bayesian formula, something like that. And you just put y tilde and then, the functional form that you think represents the conditional mean for this process. In a model like this, B1 and B2 are sort of, you could predict them with other predictors. This is saying these are both given a linear model with just an intercept, which is basically saying there's like a B1 parameter and a B2 parameter, and you're not really seriously trying to model them. But you could have some predictor Z that explains the variation in B2, in which case you could, put that into your formula for B2. You have to specify NL equal true for some reason to tell BRMS that this is a nonlinear formula. You'd think that might be self-evident, but you have to specify NL equal true. And then, what was your data? What was your prior? You get back this thing. And so Stan doesn't really care if your mean function is linear or not. It's drawing from the posterior distribution of all the unknowns either way. Here you have two margins to this posterior distribution, and we're recovering the true values reasonably well. True values were 2 and 0.75, and so we get a posterior distribution that I'm thinking this is the mean 1.94 and 0.77. That is obviously like well within estimation error of the true values that generated this. Robert.
What exactly are you doing when you say B1 plus B2 tilde 1? You're saying that they don't depend on anything else in the model?
Right. They just depend on an intercept, which is a column of ones. So really like B1 is the same for all observations, and it's just like B1 multiplied by this vector of ones. But I could have done something more sophisticated there.
Okay.
So yeah, but
what you have here is like our sort of default thing.
Yeah, although it's already non-default because it's not linear.
Right.
Yeah, I mean, it's this whole idea, and we talked about it before. We'll talk about it again when we start getting into the Stan language. That sort of any unknown can be endogenous or endogenous, depending on whether you want to try to have like predictors that explain variation in B2 from one person to the next. Or you can just say, it's the same for everybody, but the way Paul generates these matrices, you have to say it's a function of an intercept. That's not really much of an explanation, but in any event, it allows BRM to do its thing, and so you can be estimating, the posterior distribution of all these things, and you're not at all restricted to linearity. Neither are frequentist models, but frequentist estimators, once you go beyond linearity or generalized linear models, very difficult to find the global optimum, very difficult to derive what the standard errors or confidence intervals or p-values would be, even asymptotically. And whatever asymptotic results you obtain, there's just no guidance at all as to whether your confidence intervals are too big or too narrow in any particular finite sample. It's going to depend on the parameters, which by definition you don't know when you're trying to estimate, but the calculations of the confidence intervals assume that those are known because it's all about the distribution of the estimator across data sets. Paul really likes this marginal underscore effects function for plotting these nonlinear relationships. And so you can see the exponential function, you can see your uncertainty around that, you can see your uncertainty is greater when you don't have that many data points compared to narrower here in the middle where there's more values of x. And so Paul does all kinds of things with this marginal effects function that you can pass a model that was estimated by BRM, and it'll figure out what to plot or what to show you, depending on exactly what sort of nonlinearity was going on in a model like that. Another one, a little bit more complicated, but showing, so this is insurance data, sort of how much liability did the insurance company have. You can read in this. So the cumulative loss of the company was this sort of complicated nonlinear function. I forget what ULT is, but this sort of this baseline multiplied up by, there's an exponential function here, and then we have this raised to some unknown value omega. I guess dev is known, but theta probably isn't. And then this sort of baseline rate, you're saying, okay, it's a function of an intercept, but the intercepts can vary randomly from 1 year to the next. Again, we have these sort of intercept explanations for the power going on here, and theta, which is sort of the scale value going into this exponential function. Obviously very nonlinear, but for some reason, I guess probably a good reason, but I don't know really what the reason is, a structure like this makes sense in an insurance context, and you just sort of want to know the unknowns, like how much does the baseline rate vary from one person to the next, and then how intense is this function depending on what the exponent is, what's the denominator is, etc. Could specify some reasonable prior values about that based on your domain knowledge. And then you can get a posterior distribution that looks like this. For some reason, I think the line came out wrong, but you can sort of see the shape that was being estimated according to the posterior distribution of the model. Obviously, it's positive, but that was true by construction. Insurance companies sort of know, what makes them have a positive association with their liability and things like that. But it was, really just a question of how nonlinear this relationship is. How big are these exponents and stuff like that that give rise to the nonlinearity? So all of these things you can do in BRM, and quite honestly, BRM probably covers the vast majority of the use cases that you would probably encounter in the social sciences, and a whole lot more. But the reason why you can do things like this that are just sort of way more complicated than, you know, take the logarithm of both sides and like estimate a linear model is because, you know, these sorts of nonlinear expressions to, you know, explain, you know, this outcome or, you know, these parameters, how they vary from one year to the next, they're really just pasted into a Stan program, and then it compiles it and estimates it from there. And so next week, we will start talking about how you can write stuff like this, or stuff that's more complicated, or stuff that's more simple yourself in the Stan language. And then you can estimate essentially any model that you want to, even going beyond the many, many hundreds, maybe even thousands of regression models that can be constructed using BRM by just mapping this R syntax into Stan syntax. But once you get a little bit of practice for that, you don't really need anyone to map, you know, R syntax to Stan syntax for you. You can just write Stan syntax yourself to define these posterior distributions, and then condition on the data, get back the draws. Okay, so like I said, I will post a homework tonight. It'll be due in a week, and then next week we'll be talking about writing stuff, entire Stan programs in the Stan language. So I'll see you then.
Oh,